Good evening, everyone, and thank you for joining us today for our webinar on space systems engineering. I hope everyone is doing well and had a good week. I know it's Friday, so all of you are starting to unwind, but thank you anyway for joining us on this evening or morning or afternoon, wherever you are from. Today, we are very lucky to have with us Prof. Anton Ivanov from Skoltech Institute of Science and Technology, who is also the director of the Skoltech Space Center, to share with us a little bit more about space systems engineering. Do note that this is one of our last few webinars before we take a kind of go on to a break with the webinars to allow all of you to work on your projects for the International Space Challenge. So if you have any pressing questions regarding this area, now will be the best time to ask with our experts present. So do make full use of this opportunity. As usual, you guys know the standard housekeeping rules. Feel free to post your questions at any point during the webinar. If there's any point that you don't understand, into the Q&A box so that we are able to track it. You can also use the chat to interact with each other. And as usual, this webinar is being recorded and it will be shared on the learning platform after for your review and to the end of the International Space Challenge. But then, not to take up too much time, I will hand it over to Prof. Ivanov to start.
All right. Hello, everyone. Unfortunately, I don't see how many people are there, so I will have to talk to myself here. So I'm hoping that there will be questions as we go. Oh, I can see there's 33 people. Oh, okay. All right, good. Let's see. So let me start sharing my screen. There we go. And here. So, okay. So today we'll talk about space mission and systems engineering. Today is the lecture which we typically do is as an introduction to in our class, which is called Spacecraft Mission Analysis and Design. And it outlines pretty much the overall view of how space missions are conceived, built, executed, and so on. So to start with, let me present myself. I'm from Moscow. I graduated from Moscow Engineering Physics Institute very long time ago, probably right around the time that you were born. And then I went to California and I got my PhD at Caltech. And after that, for 7 years, I worked at JPL, the propulsion laboratory, where I started studying Mars. And I actually spent almost 20 years studying Mars and looking for water on Mars. We found a lot of ice there, but this is a separate lecture. Then for 10 years, I worked at EPFL in Lausanne. This is in Switzerland, where I started also with a space center. And this is where we switched from, let's say, Mars studies to CubeSats and small satellites. And this is what I'm continuing here at Skoltech. So since now, for years, I've been a director at the Space Center here at Skoltech. The kind of projects I was involved with were Mars Orbital Laser Altimeter, which created the first topographic map. And then basically I was involved with all of the Mars orbiters and some of the rovers that are now currently in orbit on Mars or roaming on Mars. Here at Skoltech, we're mostly investing into small satellites. We have some ideas about lunar satellites, but this is a little bit off because we have to frame a student project, and that's been a little bit difficult. I also participated in the mission for exoplanet SkiOps, which is now launched and operating. But again, this is yet another lecture, so I hope this convinces you that I have some experience with space projects. Let me say a few words about Skoltech. Actually, while I'm talking about this, you can point your phones on this QR code that I have created. It will point you to the description of the master programs that we offer here at Skoltech and Space Systems. There is a description and everything else. So maybe some of you are looking for a master project, and Skoltech is actually a great place to do it. The Skoltech was founded 10 years ago. In fact, we just celebrated 10-year anniversary. This is a private university on the outskirts of Moscow. And what sets apart our university is that there is no tuition fee. I don't know any other university, at least in Europe and in the States, that doesn't have a tuition fee. Everybody charges something. Not only we don't have any tuition fees, we also offer a merit-based stipend. So if you get in, then the stipend allows you to live in Moscow, rent a room or a flat, have subsistence, go and see places. So it's a very good deal. We're going to change it soon to basically no stipend, but Skoltech offers really good conditions for study, especially for the master program and for PhD programs. Most of the professors actually come from the West. So for example, just like myself, I worked in the States, I worked in Europe, and a lot of other professors, even if they're Russians, they worked somewhere like in places like MIT, Columbia, or somewhere in Munich, in London, and in other places. Some of other profs at our centers, there is a French, there is a Canadian, there is an Italian from La Sapienza. So anyway, it's a very international group of people, and the working language here is English, so everybody understands everybody. Space Center currently has 30 master students. This is basically every year. And the main project that people have worked on, advertisement in space. So this is how you deploy satellites that can show advertisement. Again, yet another lecture. Currently, we're preparing our swarm of small satellites for launch. We're kind of in the final steps of preparing for launch next year. We have a large group that's working on space weather prediction, a group of Tatiana Podlatchikova, and we are engaged quite a bit in remote sensing of the forests. As you can guess, there's a lot of forest in Russia, and we're trying to basically itemize all of the forests on all of the trees that are there in Russia. That's billions of trees. Anyway, so enough about Skolkovo for today. So let's go back to the topic. So what does a space project looks like? These pictures I took at JPL when I visited there just before the pandemic hit, when we were still allowed to travel. And you can see here, actually, this is Perseverance rover. Well, on the right, it's one of the Earth remote sensing missions, but on the left, on the left is the Earth remote sensing, but on the right is Perseverance rover, still at JPL just before launch. And here is a slightly larger picture of it. This is what it looked like when it was still back there. Now this hardware roaming Mars very successfully. There is a lot of interesting stuff coming from it. That's what it looks like, the hardware. There are many other pictures of satellites and CubeSats, or you know that James Webb Telescope is now preparing for launch, and this is a very exciting event. We're all waiting for it. This is, what the goal of today is to tell you how the projects are conceived, or how they executed, and a few related things related. So I'm going to draw a few pictures. So what makes up space systems? Let's see. There's something in the chat. Tonya, спасибо. So let's see. So we have a satellite. I'm just going to draw in here very crudely. Just a second. Okay. So let's say we have a satellite, right? And let's say, so we have some solar panels. We have a satellite dish that sends stuff down. Let's say this is a space telescope, so we're looking somewhere up. So what else do we need? We need a launcher. So I will draw a very crude rocket. Okay. Which launches a satellite, when satellite receives data, it can't process it itself. It has to link it down. So I'm going to draw a little antenna here. That Earth is somewhere in here. We'll put some grass inside. Anyway, so what happens here is that first the spacecraft launches the satellite into some sort of orbit around the Earth. And then when satellite starts, it sends down the data. This is very crude picture, of course, but this shows the main elements of just about any space system. The satellite can be, for example, something way more complicated like ISS or let's say JWST, which requires a lot more resources on the ground. It can be a CubeSat, which are much smaller things, but they still require the same elements. So no matter what the space system is, these are the three key elements. So if you look a little bit more formally, what happens when you start just about any space project, these are the main elements. So just highlight a little bit. So the mission splits into what we call launch segment, which is effectively a launch vehicle, and then there is a launch site because you have to decide where you launch from. And inside these systems, they can also split because, for example, each launch vehicle, they split into stages, and it depends on which rocket you're launching. You can either launch as a dedicated payload, just like JWST on Ariane 5, or, for example, in case of CubeSats, you can launch it as a piggyback payload on something else, on some others, so on Soyuz rocket or something else. For example, our satellites for SwarmSats, they will be launched as a piggyback on a larger Earth remote sensing satellite. So that's the launch segment. Now, then there is the spacecraft itself, of course. The spacecraft itself typically splits into these systems. So you have the structure, you have the thermal, you have the telecom, you have the payload, command and data analysis system, you have the attitude control system, you have some power supply, and you have flight software. So there is also propulsion, give it or take in some missions, but not all the time. It really depends of what your satellite does. There is, of course, the payload can split itself into many different problems. So you can see that you start growing these trees of things because each of these elements splits, into some other elements correspondingly. The ground segment typically consists of the ground station itself, which means it's basically a dish in a satellite that sends commands up to the satellite and receives data down. And there is also mission control. One element that's missing here, mission control, is oftentimes connected to the science operations center. In science operations center tells the satellite what to do. Do they want to take data in the optical, or they want to turn on the radar, or if it's a rover, they want to drive forward, or they want to drive backwards, whatever. Mission control executes commands and they make sure that the satellite is okay or the rover is okay. So, but they are responsible for communicating with the spacecraft. On top of this, there are two disciplines that are not in the hardware. They exist as people, they exist as experience, they exist as competence. Well, first of all, this is systems engineering. This is this one. This is what we do a lot here at the Space Center. And the system engineering is actually a science and a little bit of art of how do you actually tie all of these things together. You can see all of these links that connect these parts, and systems engineering is responsible for putting all of those things together. Another discipline that exists, and it doesn't exist in hardware, this is mission design. These are people who calculate orbits, who will give you constraints where you can charge up your solar panels, when you can communicate to the ground, what kind of orbit you will select, what sort of delta V's and propulsion you will need to maintain your orbit, and so on and so forth. So if you start any space project, and I guess in the framework of what you're doing right now, you are doing space project, these are the elements that you have to address in some shape or form. Oftentimes, people concentrate mostly on spacecraft and forget about ground segment, or they forget about systems engineering, or they concentrate on mission design without considering the spacecraft. So in our classes that we do here, we of course concentrate mostly on the spacecraft because the satellite is called spacecraft mission design, but we also have to address what sort of launch opportunities you will have, what sort of ground stations you will have in any real project. You have these three main parts: how are you going to launch, how are you going to operate the spacecraft, and what sort of ground segment you're going to have. Also, you have to include parts on the engineering, how are you going to maintain your documentation, how you can maintain your models. So at some point it becomes a little tedious, but unfortunately that's life. See, I can see that there is a question in Q&A. I'm not sure if I can.
So the person asked, is Skoltech currently working in design GNC systems or any type of formation fly?
Oh, actually, yes. The project that I mentioned, space advertisement, it is about formation flying. So yes, we actually do this. And GNC is a very important part. And we are building our own GNC for this form of the satellite, because actually the systems that will be engaged mostly during this warm flight is the GNC. So I can talk about this at the end. So if you're interested, I'll be happy to do it. Anyway, let's go to the next slide. System complexity. This is a little bit of a general slide, but what I want you to remember here is a rule of 7. If you think about it, an average human can remember 7 things at once. So for example, if you take 7 students for the project, I can remember as a professor who is doing what exactly. If I have 15 students, I'm sure I will forget about something. When we're doing classes in the project, we always split to roughly 7 people per project, or roughly 7 groups, such that I remember what groups is doing. So if you don't think about it much, but if you conduct some tests, just like this guy Miller did in 1956, he realized that somehow human brain, I don't know why, human brain is wired to remember just 7 things at once. And that's why it's when you're thinking about how to split your system, it's better to split it into this 7 trees. So basically each node can have 7 children. So if you think about spacecraft, typically the number of systems we have is 7, 8, or 9, so it's okay. And as you can see in my previous slide, when I split the space mission, I had 5 parts. So I had launch spacecraft, ground stations, mission design, and space system engineering. So it's 5. So 7 plus or minus 2 is something that you can remember. And if you think about complexity of things that exist in the world, airline is actually the most complex. And I have to say that the spacecraft are not as complex as a satellite. It's probably as complex as a robot, so which is automobile. It's between copy machine and automobile. So in this chart, that would be 5 levels of complexity or 4. So if you take something complex like JWST, it's probably 5 or even 6. But if you take something like a CubeSat, it's probably not very complex on this scale. So it will be somewhere near 4. So satellites occupy this kind of range of complexity where you can split everything into 4, 5, or 6 levels. So the point of this slide is not to tell you, how many levels of complexity you can have, but it's typically you have to remember this magic number 7, which allows you to split any systems into something reasonable. All right. Now, let me tell you a little bit of history about systems engineering as a science. Actually, the first systems engineering job that we know about for sure, and which actually worked really, really well, is Egyptian pyramids. If you think about how many workers you had to organize and the technologies that you had to put together and the durability of the things and complexity of those things inside, because they had all the secret chambers and whatnot. The first complex project that we know about is Egyptian pyramid that happened 4,000 years ago. And I recently started to read up about this, and I'm actually thinking about creating a small explanation of the pyramids in terms of systems engineering kind of in the modern days. But that's the first time we know that a lot of people were organized to build the things over the period of 20 or 30 years. Then during the modern age, we trace back to 1829 when to the rocket locomotive. This is the first complex systems that started to be designed, implemented, built in series, and operated for a long time. So the locomotives were actually the first system where the principles of systems engineering started to be applied, and this is where we can trace back. Formally, as a science, it starts with a few things that were developed in Bell Labs, and then at MIT, and then Rand Corporation. But really, systems engineering was starting to call systems engineering. That was in the 1960s, when NASA faced a challenge put forward by JFK, John Kennedy, to put a man on the moon in 10 years. That's back when USSR was battling with the United States for space supremacy. So the first systems engineering manuals were put together by NASA in 1960s. So nowadays, the main, let's say, body of knowledge is represented by a society that's called INCOSE, International Council for Systems Engineering. And I will refer you later on to some of the materials. If you want to read a little bit more about systems engineering and what it looks like, you can refer to materials that are published by NASA and by INCOSE. And I put them into the reference section at the end. Even if you glance through it, it will help you tremendously to prepare documentation for your project. Okay, enough with history. So how do we do things? So let's say you have this mission to launch, well, let's say relatively simple satellite that will do remote sensing, or you have a mission to fly a man to the moon. It doesn't matter. You have to have some sort of approach where you take this very complex project and you start to split it into different views. So one view I have already showed you. So you take a complex system and you start taking parts of it. So you say, okay, now let's consider separately the launch mechanism. Let's see how we think about the spacecraft and the mission system. And effectively, what you need to do is you need to find people who are specialists in rockets, who are specialists in spacecraft, who are specialists in mission design, and you start splitting this very complex problem into a set of tasks, and you find professionals to do it. And this is how you put together a project. So that's one view, right? So this is when you say, okay, this now in order to build, in order to launch a man to the moon, you need to build a rocket, a satellite, and the ground system. So this is how you start. Now, another view is actually in time, and this is what I'm showing you. So how do you actually start implementing this project? Now, here what I have to say is that this V-diagram approach is good not only for space systems, but for just about any complex systems there is. Airplanes, they are built exactly using the same system. When we're talking with people from Airbus or from Sukhoi here in Russia, I show them this V-diagram. Oh yes, of course, this is exactly what we do. So all the complex systems in the world, even automobiles, airplanes, spaceships, they're built using this same approach. I'm going to go through this V model. I hope that it's not going to be very boring, but if it is, you let me know. Well, first of all, we always start with stakeholder analysis. So for example, if we want to launch a person to the moon, John F. Kennedy formulated it really well. He wanted in the duration of 10 years, he wanted 2 humans to be placed on the surface of the moon, walk there for a couple of days, and then come back. And actually, at the time, the money was no object. They could spend how much they wanted because the United States need to beat the Russians to get to the moon first. So the stakeholder wish was to be at the moon, to have the man at the moon before the Russians. That was the stakeholder expectations, which in this case was John F. Kennedy, who was the president of the States in the 1960s. I have to say that eliciting stakeholder expectations in realistic environment is actually a very difficult thing to do, because there are many cases when stakeholders or people or your customers, they have expectations that they don't tell you. And you have to really sit down with them, conduct a lot of interviews to figure out what is it exactly that they want. In things as benign as we have now an education system for one of the Russian companies, and we really had to sit down with them and understand what is it what they want to learn, which was very difficult to do, and we're still not sure that we understand them really well. Anyway, stakeholder expectations is very, very important. But again, there is another whole lecture about it. I'll be super happy to tell you about it because this is something that I really like. Anyway, but maybe another time. Then you go into definition of high-level technical requirements, because in the end you have to formulate your project in the series of statements where you say we want, a two-person crew to be at the moon, to walk there, to exist there for a couple of days, to do a few other things. Let's do this. Right. So you have to formulate them. So how to formulate requirements, how to make sure that they are verified and then validated. This is the whole process that actually happens as you go through down the left side of the V diagram. Because oftentimes what happens is you start looking into architecture and you start evaluating technical details of the project. It turns out that you violate some of the requirements, so you have to go back here, reevaluate your top level requirements, and do it more than once. This is called iterations. Sometimes once you have selected a concept and you start looking into even finer details, so this happens during the system optimization and final documentation, you still find that there is some key technology missing, or you violate the budget or something else. And you have to go back either to the previous step or all the way back to here. And sometimes, actually, what happened with some projects, you had to come back to the stakeholder analysis, and you have to tell your stakeholders that the project is not possible at all. Concept creation is yet another things, but actually my first slide, when I showed you the rocket, the spacecraft, and the ground station, this is an architecture. So this is for some realistic things, it's a much more dedicated exercise. Also, we teach how to do this at Skoltech. And we can show you various you can actually have trade-offs between different architectures, because some architectures become a bit more expensive, some don't satisfy all of the stakeholder expectations. So anyway, there is some science behind that as well. Behind concept selection, it's the same deal. It's more detailed of the project. So the V diagram in the end, what happens here is that you start on the top level of the project and you go down and down and down and down to the point where you start drawing stuff. When you start preparing documentation, when you start prepare drawings, when you do a lot of modeling, because, well, for example, in case of the satellite, you have to prepare you have to prepare a structural model for your vibrations. You have to put together the thermal model. You have to prepare flight software, so you have to program all of your things. You have to address issues in electromagnetic compatibility, because your attitude control system starts influencing the computers that you have on board and the other way around. Or you have some very fancy payload that basically shortens the whole satellite, so you have to address that. So there are lots and lots and lots of details that have to address at this system optimization and concept level. Again, we know how to do this. It just has to be done. So once you have ironed out all of the details of your project, and actually here there are a lot of prototypes that are being created, because at this level you can identify technologies that are more critical, and you say, okay, it will be much faster if you just create a prototype and test the hell out of it, as opposed to modeling it. So there is always a trade. Do we want to actually go ahead and implement the system, or we do modeling it in the software? And sometimes it's easier to model, and sometimes it's easier to make a prototype. So it really depends. And this is something, this is a trade the system engineer has to do all the time. And yes, the stuff is difficult, and you commit people, you commit resources, you commit, the worst of all, you commit time. And sometimes you build a prototype, it doesn't work out, or you start doing model and you spend a lot of time modeling and you don't get the results that you want. So it's tricky. It's the space system is are tricky. And actually, it's the same. If you consider an airplane, it's the same exercise but it's a little bit more complex in terms for the airplanes than it is for the satellite. Once you know exactly what you're doing, you start manufacturing and integration. So you start actually doing it. You start making sure that interfaces are all there and the parts fit to each other. And when you turn on the system, it actually works. Then you go to the next step, which is verification and validation. Now, what you do in verification and validation is actually quite simple in words, but not so simple in reality. So what you have to do is you have a list of your requirements here. Well, my iPad is old, so it does not draw really well. So what you have is you have a list of technical requirements and lines, and then you have a test. And basically, after each requirement, you have to put a check mark. That requirement is validated, the requirement is validated, the requirement is validated through testing or analysis or demonstration or something else. that's the part where you realize that your tests are failing, that some parts don't fit, then you have to change your system a little bit. But once you do a change, it affects the rest of the system. And sometimes you have to go back to technical evaluation, you have to re-optimize the system. So you basically have to redo the whole thing to make it work. And only after you have cleared through all the testing, then you satisfied stakeholder expectations, you can go and you can go forward with implementation and use. Once you launch the project into series, you start lifecycle management and utilization. And it's actually mostly for the airplanes, because airplanes go through 40, sometimes 50 years of utilization. So you have to maintain them, you have to fix them. And not so much in terms of satellites, because satellites typically survive between 1 year and 15. There is not much you can do about it. I mean, there are cases where you can fix satellites like Hubble, but it doesn't arrive too often in the space business. So anyway, when you do any project, you have to follow this V diagram, and you will be okay. And especially when you present to professionals, if you show them that you followed, at least, I mean, probably you won't do the integration and manufacturing, but in your project, you will probably have to go down through this V diagram. And quite possibly, if you follow this route, then you will be fine. You will be fine, and everybody will understand what you're doing. So the new, well, not it's actually not very new, but important is model-based systems engineering. This is a relatively modern approach. Well, I'm struggling with modern because we've been discussing it for more than 10 or 15 years now. But everybody is now using model-based systems engineering. People are calling model-based different things. There is also a concept of digital twins, which is highly debatable, but this is sort of the frontier of systems engineering right now. So we're still working on the exact definitions of things. So anyway, if you're interested, you can always contact me, or you can, yeah, I guess you can contact me and I'll tell you a bit more about it. Or maybe in the framework of the school, I can give more lectures on any of this topics. Now with the slide, it's very busy. I'll walk you through it, but then I think I'm going to give you a copy of my lecture, and then you can look at it at your own free time. This is how space projects are organized. I have to say that airplane projects are organized roughly in a similar fashion. Maybe things called differently, and at least in European Space Agency, NASA, and to some extent Roscosmos, they're doing everything following these different phases. There are some differences between ESA, NASA, and Roscosmos, but 90% is here on the slide. So all of the projects are split into phase 0, A, B, C, D, E, and F. And what you're doing is probably phase 0, A, maybe phase B. So these phases are named conceptual, then feasibility studies and design definition, where you go into details. Then there is phase C, when you actually prepare manufacturing plans. Then in phase D, you actually manufacture your satellite. This is the most expensive phase. Actually, phases C and D are the most expensive. They sometimes overlap. Now, once you finish this phase D, you launch and operate your spacecraft, and then you have to dispose of it. And it's important nowadays because people are talking quite a bit about space debris and how you handle it. So phase F became recently focal for many activities. For example, in Switzerland. Now, to jump from one phase to another, you have to pass through a review. So, for example, from phase to go from phase 0 to phase A, you have to complete mission design review, and then from phase A to phase B, you have to pass through preliminary requirements review, and then to go from phase B to phase C, you have to pass the famous preliminary design review. This is where many projects are stopped, by the way. So this is famous PDR. And then the most important review in the project is CDR, which is called critical design review. This is where you sit down with stakeholders, and this is a place where you go from a paper project to a real project. This is called the CDR. Then during phase D, there are many different reviews. There is qualification review, acceptance review, flight readiness review. And there are many more. For every test, there is a review. So there are many different reviews. From phase E, there are not so many because the satellite was already flying and operational. So these are operational reviews, some commission reviews, and so on and so forth. Now, what does system engineering do? So I have highlighted here sort of documentation that you need to provide for any of these phases. So for example, if you're working on a phase 0 project, you just need to produce a high level specification and mission definitions. So it's typically just one document that tells you, okay, we want to go to the moon. You have some concept of operations. So for example, during the Apollo, you put a satellite into orbit, and then it waits for the lunar module to ascend, and then this is what takes them down to the ground. So this is kind of things that are, it's a high level description of a mission that you do. But then for phase A, you need to come up with many more documents, such as preliminary system analysis, technology identification, design trade-offs, preliminary baseline design, preliminary assembly integration and verification plan. So it becomes a bit more detailed. And the number of documentation actually grows as you go from phase to phase. You have to maintain this documentation and all the steps. So actually, one of the very tedious things about systems engineering is to maintain all of the documentation, maintain all the format, maintain all the information, knowledge management. It's very tedious. It's not fun, but it has to be done. It just has to be done. Anyway, so I'm going to move forward a little bit because we'll start to run out of time. Now, I'm bringing this up to show you that, look, we now have more than 60 years of experience with space systems and space systems engineering. And one could say, well, you know what? By now we should figure it out. By now we should figure it out, and everybody has to fly safely. There should be no more accidents. We know everything, and forget about it. But this is not true, and we know a lot about various accidents that still happen despite of systems engineering. So, for example, there is a very famous Challenger shuttle disaster in 1996. Then there was very unfortunate Columbia accident in 2003, which actually made NASA to reconsider many of the practices because at some point people started to overlook certain things. Another example is the recent fiasco with Boeing 737 MAX, which yet another story that I'm not going to talk about now, but what I want to highlight, despite of all of the system engineering rules and practices and experience, you still have failures. And typically failures, they are due actually human factor, because there's always a person in the loop. There are people making decisions, and sometimes people make decisions under pressure, and sometimes they make bad decisions because they are under pressure from stakeholders, or there is just an engineering error, just like in the case of this O-rings, which were failing during the Challenger disaster. So what I'm saying is that, yes, there is a body of system engineering, but still the human factor is huge. And this is what makes people to make mistakes. So this is where it becomes art, the system engineering. So if you do any project, not just space project, you will find that if you do everything correctly, then the risks will be low, but cost will be very high. And your stakeholders will say, look, guys, this is a point when we have to take a lot more risk. And let's say we will launch something and risk it. This is how Elon Musk is actually doing it. Look at how many failures Elon Musk has allowed to happen with his rockets before he started launching something. But this is, unfortunately, during the real test, this is the only way to learn. You can do a lot of tests, you can do a lot of subsystem modeling, but only when you put the whole system together, you launch it. This is the only way to learn things. So anyway, so the art is actually keeping it proper and documented while keeping it under constraints of the cost. So this is where systems engineering becomes art. What is there that's new, and how can you innovate in the space sector? So yes, there is Elon Musk, there is Jeff Bezos, there are other people now, and what people are trying to do now, and this is sort of the frontier of systems engineering. What you want to do is to put a lot more emphasis on the early phases of design and trying to get those right. So if you see, this is basically the number of changes that was written in one of the projects. So this is time is here. And to some extent, every change here incurs some cost. So to some extent, this graph is showing the cost that incurred because something did something wrong. So in a lot of cost is incurred here during the manufacturing. So what you want to do is to move these things back to paper phase here. And basically what you want to do is you want to make your models, to get your models right before you do it. So how do you do it? Well, first of all, you have to think about the life cycle of the system, where you have to include operations and disposal. You start using new approaches and methods such as model-based systems engineering. You do parallel design, formal programming methods, and you have to educate constantly your engineers. So this is exactly what we're doing at Skoltech. So we study model-based systems engineering, we have concurrent design, we study some of the formal programming methods. So we try to help the industry improve its methods to make it, to actually fit the space systems under cost. So that's very important. I'm actually almost done. I don't think I have time to discuss gentry least critical behavior. I'll just introduce them and then you will just look at them by yourself. Let me just let's try this. One of the best systems engineering I knew is Gentry Lee from JPL. And he introduced these characteristics as the best properties, the best characteristics of a systems engineer. Gentry Lee has spent more than 40 or 50 years at JPL. He was involved with all the missions at JPL, and he was the best system engineer I ever knew. I'm not going to talk about this now because we're running out of time. Rather, I will go on to references, and you can take a look at the slide later. If you have any questions regarding this, I'll be happy to answer it. The only thing I would like to highlight here, I think it's the one that I like, is all systems engineers have to have a proper paranoia about the project. You have to expect the best, but plan for the worst. Another saying that we had at JPL is the hope is not the plan. So whenever you're planning for something, you say, well, we hope the parts will arrive on time. Well, you have to plan for the parts not arriving on time, things like this. All right. References. What can you read further on the subject? Now, the easiest is to Google NASA Systems Engineering Handbook. That's basically a Bible for NASA engineers. It's very thorough. You can build a lunar mission using it. But if you do it exactly by the book, your project will be very expensive. So the trick is to take the best practices inside the NASA Systems Engineering Handbook and try to modify them for your project. Another body of knowledge is INCOSE Systems Engineering Handbook. And the INCOSE book is applicable to space systems as well as to another system, because the NASA Systems Engineering Handbook was written for flight systems, and you will see a lot of things that are referenced in space. INCOSE did a really good job in trying to take the space out of it and make it applicable for things like, I don't know, elevators, cars, airplanes, other complex systems, excavators, cranes, things like this. So INCOSE is a bit more general, and I think it's a little bit easier read compared to NASA Systems Engineering book. There are many other books that are available on the internet, but I think this is a good start for your projects if you look through them. There is also ECSS standards that help you to put together documentation for your project. But again, this is a subject for yet another lecture, because I don't want to bore the hell out of you with my first only lecture. I'm going to stop here, and I'll be happy to take any questions.
Thank you, Prof. Actually, we do have a question. Someone is asking if you could elaborate more on the Formation Fly project by Skoltech that you mentioned earlier on in the webinar.
Let me look for something real quick. I think we have a movie somewhere. But I don't think I will be able to find it. As I'm looking for it, some time ago, we had a guy from an advertisement agency approach us, and he asked us a very interesting question. He asked us, Anton, can you help us out with a space advertising project? Which means, so what we offered him is that we say, look, we can fly our satellites information like a letter. So for example, some very easy logo, Pepsi, Coke, or for example, Skolkovo SK, you can fly information like a letter and reflect sunlight back to the ground. And this way you basically do advertisement for a brand. I'm just trying to look very quickly for presentation. Let me check if I have it. So it's not here. So anyway, and we've written a couple of papers about it. It's probably no. PDF. Anyway, so the trick is that all of your satellites, they are moving in obviously circular orbit around Earth with 7 kilometers per second speed, and you have to organize your orbits in such a way that they're phasing relative to each other very slowly for forming these letters. And it turned out that's not an easy problem to solve. And one of my students, Shamil Bektimirov, he's working on it. He's finishing up his PhD thesis. So if you want to know more, then you basically have to talk to me, and I'll show you what we're doing. I'll point you to a couple of papers, so I can give you stuff to read.
I do do have a follow-up question for that, which is what are the benefits of formation flying? What are some of the benefits of formation flying versus a regular constellation?
So that's actually the point of our swarm of satellites project. Up to, let's say, year 2010, most of the satellites, my AirPods ran out, so I have to. Right until 2010, most of the satellites were just one satellite. And the problem with just one satellite is that it becomes very big and it just looks at one place at a time. Nowadays, mega constellations are needed because you have to provide worldwide internet, or if you want to monitor CO2 everywhere in the world at the same time, you need to have many, many, many satellites. And of course, you want to have them distributed properly in orbit, and it becomes fairly expensive. So the goal is how to make these fractionated systems complement each other, make sure that they can provide you the information you need, do it in certain cost, and make sure that they synchronized. So this is what formation flying is for. Another application is when you want to form very large aperture for radars. So you need to have effectively thousands of satellites fly in a dish pattern, which is also very difficult to control. So that's another application. So either you maintain a formation, for example, you need to remain in a circle and you fly it like this. That's one application. Or another application is when you have to cover the whole Earth with imaging at the same time. So that's another application. So this is something where a lot of people are moving to, and especially with CubeSats, that's definitely an application for them.
Someone is asking if would it benefit to have a formation of satellites each with a different kind of a payload, meaning that each satellite would be able to run a different function and then have it work together, collect different sets of data and then use that data together?
It depends on application. It depends on application, depends on your stakeholder expectations. But I'd say that typically what you want from many points is that all of your satellites in your formation look exactly the same, because that helps you with manufacturing, that helps you standardize your processes, that helps you maintain the satellites. And typically what you want is, for example, if you have a radar detector and if you have an imaging detector, you want these detectors to observe the same information at the same time. Because, for example, you can fly with a radar and you find a ship somewhere, but when you fly it 2 hours later with an optical instrument, the ship is not there. So you're missing on the information. But again, depends on application, depends on what you want to do. The first goal is everything is the same, but then you talk to your stakeholders and see what they want.
Thank you. Does anyone else have any other questions for Professor Ivanov? This is your time to ask for those who are already working on your, I know, satellite projects, or even those who are working just on standard missions, experiments to the ISS. This is a great time to check in and ask any questions you have or clarify anything about your projects.
Well, I think I'm going to send my presentation to you, Jillian, right, so that you can share it. And if anyone has follow-up questions later on, I think they can send them to you and you can forward them to me. And I mean, that I can ask some of the questions later if somebody is interested.
Is there any slot if I want to do a master at Skoltech and want to work on GNC?
Somebody is very keen on this. Yes, we will open. Obviously, the year has just started. I think we're opening the first wave in March, maybe even early, a little bit early in February. And you just go to this website that Antonina posted in chat, and you apply, go through interviews, and you can start in September 2022.
We will be sharing the presentation via the learning platform. So everyone who is asking for the presentation, don't worry about that. If you have any other questions for Prof. Ivanov or any further ways you would like to ask him after this webinar, feel free to send your questions to me. I can forward it to Antonina or Prof. Ivanov himself to reply via email if that is easier for everyone as well. But yes, is this for the, so for people who are asking if this is for the starter category also, yes, this is a lot more towards satellite missions, but a lot of the concepts that Prof. Ivanov has taught today can also be applied to any space mission, right? Any space mission, things that you need to take into consideration when designing any experiment or satellite mission that you are working on.
Yeah, even if you do an experiment on ISS, I mean, the whole thing applies as well, because you still have to elicit stakeholder expectations, you still have to provide technical concepts, you still have to provide technical subsystems and formulations, and there will be a lot of requirements that will come from the ISS side, because you can't use certain materials, you can't use certain batteries, you can't use a number of things. So yes, it absolutely applies for even the payload or an experiment.
Yes. So yeah, so for those who maybe are working on the star category challenge statement, this is also very applicable to all of you to take the concepts away and learn from. If there are no other questions, I don't want to hold Prof. Ivanov up any longer. Could you suggest the software tools other than SDK for analysis?
Yeah, SDK is a beast. Well, unfortunately, no. For mission analysis, so far, SDK is the best. We're actually working on a mission planning tool, which is similar to SDK, and it's based on SPICE kernels. Actually, if you want to do something, let's see if I can send it to everyone. I'll send you a link to a library which I'm using a lot. It's actually, this library comes from JPL, it's called SPICE. It's very useful for understanding concepts of mechanics, and you can program it yourself in Python or in other language. But since it's open source, it's much more, I mean, there is a learning curve to it, because in SDK, you just go and you pull together things from different sources and it comes all together very quickly. But of course, at some cost. But if you want to do it, let's say for free, download SPICE. There is a lot of documentation, tutorials. It's been around for 20 years. All of JPL missions are flown using SPICE, all of them. So if you trust JPL, you can trust this library. And there is actually another toolkit that my students were using, but I forgot what it's called.
GMAT, General Mission.
Yeah, GMAT. Yes, GMAT. Yes, GMAT is also very good. But I actually, for everything I do, I actually prefer SPICE. It's much more professional compared to SDK. Of course, visualizations are better with SDK, but
yes. So if some of you have missed it, we do actually have a tutorial for GMAT up on the learning platform that you can refer to. Obviously, as Prof has mentioned, SDK is, if you are able to get access to SDK, it is definitely a lot more user-friendly in a sense, because a lot of things is already programmed in. but it does require a license that you need to pay for. Although I do think they do have a free trial, a 2-week free trial.
Yeah, well, I think, well, the last I checked, they have a free version, which is very basic, but you can do basic analysis on it. But once you try to do something interesting, you have to pay for it, yes.
Yeah, so there are still ways to get access to SDK. If you want to try that, you just need to kind of look. I think they have a free web version, they have a free trial version that you can download as well. Otherwise, there's, like we mentioned, there's Spice, there is GMAT that you can try as well. So there are different softwares online, just kind of play around to see what works best for your team and your project. And yeah. Do we have any other questions?
Yeah, I think GMAT is fine. It's somewhere halfway between SDK and Spice. I mean, Spice is really hands-on programming, and SDK is a beautiful user interface, although they are stuck in year 2005. Yeah, and GMAT is a bit more advanced. Yeah.
Otherwise, I don't think we have any other questions. Thank you so much to Prof. Ivanov for the lecture today. It was very insightful. And I hope you guys managed to take away a lot of important information from today's lecture. I can see this being very useful for a lot of you working on your projects. So hopefully you do take away some key pointers that you have to keep in mind when working on your proposals. We are about slightly less than a month away from submission deadline, so good luck to everybody. Yeah, otherwise, I hope, Prof. Ivanov, you have a very good afternoon, a happy weekend to everyone, and thank you everyone for joining us today.
Yeah, cheers.
Thank you so much, Prof.
Yeah, bye-bye.
Bye.
Thank you, Antonina. Thank you, everyone.